Hello, I welcome you all in this presentation. And in the previous lectures we have talked about the ways by which we can understand the weldability of metal, and especially the weldability of metal is affected by the three important parameters like the welding process, the purpose for which the weld joint is being developed, and the fabrication conditions under which a joint is to be developed. And there are three main ways which can be used to assess the weldability. One is like the efforts that we have to put in to produce a sound defect free weld joint, and the second is the quality of the weld which is produced, and third is the cost related aspects. Apart from this, in the previous lecture we have also started that how the metal properties affect the ease of welding or the weldability, and under that we have talked about the effect of the physical properties like thermal expansion coefficient, melting point, boiling point of the material, thermal conductivity of the materials. So, those were the some of the properties about which we have talked with regard to their effect on the weldability of metals. In this presentation we will be talking about the three or four other aspects related with the metal properties and their effect on the ease of welding or the weldability of metals. So, among those the characteristics about which we will be talking includes like the metallurgical properties associated with the material, like what happens when a metal is subjected to either heat during the fusion welding or plastic deformation during the solid state joining process. The second is the chemical properties, which is primarily about the composition of a given metal system. So, since the composition affects the microstructure and oxidation tendency, the way by which it will be reacting with the surrounding gases at high temperature, it also affects the corrosion behavior, and especially when the metal is subjected to the localized heating or the controlled plastic deformation during the welding. So, we need to relate the composition of a given metal with the ease of welding. So, using those characteristics related to the chemical composition, we will be trying to talk about the effect of the composition on the weldability of the metal. And then there is another important aspect that is affecting the weldability of metal is the strengthening mechanism. Each metal system is designed using a particular kind of the mechanism. So, what are the various mechanisms which are used for developing the required strength in a metal system, and when the metal system developed or strengthened by a particular mechanism, how does it behave when it is subjected to the welding, either through the fusion based approach or through the deformation or the plastic deformation based approach. So, mechanisms like solid solution strengthening, work hardening or the strain hardening, then the grain refinement, transformation hardening, precipitation hardening, and the dispersion hardening. These are most commonly used mechanisms or the underlying mechanisms which are used for strengthening the metal systems, and response of the welding with regard to the heat or the deformation to these mechanisms is found different, and which in turn affects the ease of welding of the metal. Then the mechanical properties of the material which is being welded. So, this is another aspect like metallurgical properties, the mechanical properties of the metal which is to be welded. These properties also play a big role, especially in case of the solid state joining, where the plastic deformation plays a key role. Like if the metal can have the yield strength of the 200 MPa or percentage elongation, say 40% elongation. this material will behave completely in different way as compared to the another metal system which is offering the yield strength of the 1000 MPa, and the ductility it is just the 5% in terms of the percentage elongation, because these two characteristics or these two mechanical properties of the material will significantly be governing the flow stresses or the flow behavior of the material, and which in turn will be affecting the plastic deformation tendency of the material, and the change in the flow behavior and the plastic deformation tendency of the material will be affecting the ease of welding using the deformation based approach, where either the micro level plastic deformation is used or the macro level plastic deformation is used. Certainly the role of the mechanical properties on the fusion based welding processes, means the weldability of the metal by the fusion based welding process is not influenced by the mechanical properties. So, based on the approach which is being used for the welding purpose, that will be significantly determining the extent up to which these properties of the materials will be affecting the ease of welding. Now, we will be talking about these characteristics one by one. Like the first one is the metallurgical properties. So, with regard to the metallurgical properties, if we say take one metal system A, what happens to it when it is subjected to either the fusion through the application of the external heat from the external source or through the controlled plastic deformation, that altogether depend upon the kind of the metal system and the strengthening mechanism which is being used for design, which has been used for design of a given metal system. So, if the fusion based approach is being used, then it will be leading to the cast dendritic structure, and it will not have any effect of any other strengthening mechanism which was used for developing the required strength in a given metal system. But apart from that, there will also be a formation of the heat affected zone due to the dissipation of heat from the weld pool. So, heat affected zone formation. So, these are the two integral part of any fusion welding process, where one weld metal will be formed and one heat affected zone will be formed. But what kind of the metallurgical transformations which will be taking place as per the kind of metal system, it may be leading to the formation of the various types of the phases as per the approach of the welding being used. These phases may be soft or these may be hard. So, formation of the soft and hard phases either in the weld metal or in the heat affected zone will be leading to the hardening or the softening of the weld metal or of the heat affected zone. So, if hardening is taking place, then of course there will be increase in strength and increase in ability of the material to take up the load, of course with the cost of at the cost of the toughness and sometimes also at the cost of the ductility. But on the other hand, if the softening is taking place, then it will be forming the weak zone, and weak zone will be leading to the eventually fracture under the external loading conditions. Say for example, here in this case this is the weld metal, and if the hardening of the weld metal and heat affected zone is taking place, then it will be showing us the increase in hardness both in the zone near the heat affected zone as well as in the weld metal. So, this is the case where weld metal is getting hardened due to the formation of the hard faces. On the other hand, if another metal system under the influence of the heat which is being supplied for the welding purpose, and if the soft phases are being formed, then it will be leading to the significant reduction in the hardness. This is the base metal hardness, and as we approach towards the weld center, you will see there is a drop in hardness. So, this drop is attributed to the formation of the soft phases, and the weld metal will be weak. So, as per the kind of the metallurgical transformation or the kind of phases which are being formed, it will these will be leading to the hardening or the softening, and accordingly under the external load, if the softening is taking place, it is the weld metal which will fail, and if a hardening is taking place, it is the base metal which will fail, or the fracture will be occurring from the base metal. So, this is one of the aspects related with the kind of the phase transformation which is taking place. Sometimes what we see that during the metallurgical transformation, some of the precipitates are formed, or sometimes intermetallic compounds are formed, and these formation of these precipitates and intermetallic compounds either in the weld metal or in the heat affected zone will be leading to the localized enrichment or the deficiency of the alloying elements. Like say this is one grain, this is another. So, we may notice that some of the precipitates enriched with the particular element is being formed at the grain boundary, while the grain is getting a deficiency or depletion of that particular element. So, this kind of the chemical heterogeneity promotes the corrosion tendency of the material, and sometimes the stress corrosion cracking along the grain boundary is also encouraged, and this happens especially in the cases where in cases like stainless steel and austenitic stainless steel, where weld decay is observed. But the underlying reason behind this kind of the undesirable effect is the chemical heterogeneity, and which will be occurring primarily due to the formation of unfavorable precipitates and intermetallic compounds. These precipitates and intermetallic compounds can also be of the undesirable geometry, like shape and size may be highly unfavorable, which is will be falling under the metallurgical transformation leading to the formation of the undesirable grain structure. So, if the precipitates or the intermetallic compounds are being formed due to the application of the heat during the welding or the deformation during the welding, it will be leading to, and if it is leading to the formation of the needle shape or high aspect ratio intermetallic compounds and the phases in form of films or the plates or needles, then these intermetallic compounds or the precipitates will be acting as a point of the stress concentration, especially at the leading edge of the needles and the such kind of the plates and the films which are being formed. And the increased concentration being offered by these the intermetallic compounds and phases at the particle matrix interface, that will be promoting the formation of the voids, and easy crack nucleation. And so, if such kind of the precipitates and intermetallic compounds are being formed having the higher aspect ratio, having the needler structure or the plate shape structures, which will be promoting the higher stress concentration at the particle matrix interface, then that in turn will be reducing the ductility, that in turn will also be reducing the toughness, it will also be reducing the fatigue resistance of the weld joints. So, this is one aspect, like whether the soft and hard phases are being formed, or the kind of heterogeneity, chemical heterogeneity is being promoted due to the formation of the precipitates and intermetallic compounds, and the kind of shape of these precipitates and intermetallic compounds which is being formed, that will also be affecting the ability of the material to take up the external load with reasonable ductility or with the reduced ductility. So, as per the kind of phases which are being formed and their grain structure, the ability of the weld joints will be changing significantly, and that in turn will be affecting the weldability. So, if the ability of the material to take up the service conditions is improved due to the favorable metallurgical transformation, then this will be leading to the improved weldability, and else the weldability will be adversely affected. Further, all the metal systems do not respond in equal way to the application of the heat being applied during the welding. Like say whenever the heat is applied for melting the fine surfaces through the external heat like use of arc or laser, so the fusion is realized. If we will see the zones near the fusion boundary, these will be experiencing the high temperature at very high rate and that temperature will be decreasing. So, this variation in temperature as a function of time, this is temperature, this is known as weld thermal cycle. So, this is the kind of variation in the temperature which is observed, and this cycle will be different for the different points, like say for point 1 and point 2. This is one weld thermal cycle for point 2 will be like this, which is away from the fusion boundary. So, this is for point 2. Greater is the distance away from the fusion boundary, lower will be the peak temperature and lower will be the rate of rise in temperature, and then the temperature, the rate at which temperature will be decreasing will also be lower. So, this is what is called weld thermal cycle. Now, whenever there is a heating and then soaking as per the kind of a weld thermal cycle, followed by cooling. So, this heating and the cooling will be affecting the metallurgical transformation. All the metal systems do not respond in the same way to the metallurgical transformation when the weld thermal cycle is imposed, and that is why as per the nature of the material systems, the metallurgical transformations will be different for a given weld thermal cycle. Apart from this, some of the phases which are formed during the metallurgical transformations, like in case of simple carbon steel, if the metallurgical in case of the low carbon steel, if it is just the ferrite and the pearlite kind of the phases being formed, the residual stress development is very limited. But if the martensitic transformation takes place, which occurs with the increase of a specific volume, and this material is very hard, very brittle and of the low ductility. So, at microstructural level it develops the residual compressive stress, because wherever the metallurgical transformation from the completely soft phase to the hard phases takes place with the increase of a specific volume, it leads to the development of the residual compressive stress wherever it is being found, but the region all around that will be under the tension. So, metallurgical transformations also contribute towards the development of the residual stresses, and to take care of these residual stresses so that their adverse effect on the performance of the weld joint can be reduced, we carry out the post weld heat treatment. So, if the metallurgical transformation is such that huge residual stresses are being developed, then we may require the additional steps to reduce the magnitude of the residual stresses, so that the performance of the weld joint in service can be enhanced. So, addition of the additional post weld heat treatment in order to enhance the joint performance will be lowering the weldability, and if the weld joint is developed without much of the residual stresses, so there will not be any post weld heat treatment requirement to take care of the residual stress related aspect. That will be offering certainly the better weldability. So, because we know that more the precautions, more the efforts, more the steps are required for producing a given weld joint, which can serve the intended function, lower will be the weldability of the material. Now, we will see the next property of the material. We know that if we say chemical composition which considers the alloy composition. So, a metal which is to be welded, its composition certainly plays a very big role in determining the weldability. Metal can be pure or it can be of the eutectic composition or other composition. So, we know that the pure metals and the eutectic alloys of the eutectic composition will be melting and solidifying at a constant temperature, at a single temperature. So, this is very good side where the solidification starts and end at one temperature. So, when the pure metal or an alloy of the eutectic composition is welded due to the melting and the solidification at one temperature, this leads to the development of the minimum welding defect related tendency, and that is why they offer a good weldability as compared to the alloys where the solidification takes place over a range of temperature. So, the alloys offering a solidification temperature range, or you can say wider solidification temperature range, there will be increased tendency for the solidification cracking, there will be increased tendency for the liquefaction cracking. So, and there will be increased tendency for segregation of the alloys or chemical heterogeneity. So, our metallurgical heterogeneity will exist, mechanical properties will also be changing significantly from the weld zone to the heat affected zone, and that is why there will be more problems related with the welding, especially in the alloys which are having the wider solidification temperature range, and those problems will by and large be absent in case of the pure metals or the alloys of the eutectic composition. So, as we have and its effect we can directly observe in case of the solidification cracking tendency during the welding. So, in that case now, yeah, like say this is the weld metal. So, the solidification begins at the fusion boundary and it progresses towards the center line of the weld like this. So, obviously the things which solidify first are in pure form, and the excess of the alloying elements, in case of the alloys having the wider solidification range, the alloying elements are rejected in the liquid metal. So, as the solidification progresses from the fusion boundary towards the weld center, what we will notice that alloying element concentration will keep on changing, and alloying elements will be enriching, especially in the left out liquid metal, and at the end we get the high alloyed molten metal. And we know that the pure metals have the higher solidification temperature as compared to the metal having the, or molten metal having the higher concentration of the alloying elements. So, that is what we can see simply from any phase diagram. Pure metals will be solidifying at a higher temperature, then our liquidus will be decreasing with the addition of the alloying elements. So, the same concept is applicable here also, where with the enrichment of the alloying elements in the liquid metal, their solidification temperature will keep on coming down. So, this in turn subsequently leads to the development of the solidification crack, and this is happening primarily due to the presence of excess alloying elements at the weld center line, and the same is also the reason for the liquefaction cracking, where lot of chemical heterogeneity existing at the grain boundaries leading to the wider solidification temperature ranges, even in the heat affected zone, increasing the liquefaction cracking. Chemical heterogeneity also promotes the corrosion tendency. Like I gave one example where either the enrichment of the alloying elements at the weld center is taking place, or in the heat affected zone some unfavorable metallurgical transformation is taking place, where the phases which are being formed are enriched with the particular kind of the alloying element, and the nearby we are having the deficiency of that particular element. So, such kind of the chemical heterogeneity will be promoting the galvanic corrosion. Somewhere it is deficient and somewhere it is enriched. So, wherever it is more as compared to the another location. So, like in case of the austenitic stainless steel, chromium carbide is found. So, these particles having the higher chromium as compared to the other areas where chromium is absent or it is in reduced quantity. So, wherever chromium is less, in case of the austenitic stainless steel, this will be acting as an anode and these particles will be acting as a cathode. So, the chromium deficient areas will be experiencing the loss of metal in the favorable corrosive environment, and that will be promoting the corrosion of the weld joint, especially in the heat affected zone. And the primary reason behind this is the chemical heterogeneity, which is being promoted due to the metallurgical transformation. We know that the chemical composition of the base metal directly affects its behavior and response to the heat treatment, and that is what we can say with regard to this plain carbon steel. We know that if the carbon content in case of the steel is increased, we will be seeing that the ferrite concentration will be decreasing and perlite concentration will be increasing, like say this is 0% carbon, this is 0.8% carbon, and say this is 1.2% carbon. So, when the carbon is absent, we have the 100% of the ferrite and perlite is 0, and as the carbon content keeps on increasing, our perlite fraction will keep on increasing and it will become for eutectoid composition it will become 100%, and thereafter Fe3C is iron carbide starts appearing, and then this entire zone belongs to the perlite. So, perlite fraction will start decreasing and the iron carbide or the cementite fraction will start increasing beyond the 0.8% carbon. And if we see its effect on the properties, mechanical properties, there will be continuous increase of the hardness with the increase of carbon content, and there will be increase of the strength up to the eutectoid point, and thereafter strength will start decreasing, while the ductility and toughness both will be decreasing with the increase of the carbon content. So, both mechanical properties and the microstructure are affected by the composition. I have this is just an example for the carbon steel, and likewise it will be happening in other cases as well. So, since the phases microstructures have direct effect on the mechanical properties, low carbon steels having the lower strength, higher ductility, while high carbon steels will be having the higher strength and the lower ductility, and that is why. So, this is ductility, tensile strength, and this is hardness. So, so it will be easier to weld the low carbon steels by the deformation based processes as they have the lower yield strength and the higher ductility as compared to the high carbon steels. While in case of the fusion welding, the role of the mechanical properties probably is limited to the development of the residual stresses. For example, the metals of the high yield strength like 1000 MPa, it can develop the maximum residual stress also of the 1000 MPa. On the other hand, another metal having the maximum having the yield strength of the 350 MPa, then the residual stress magnitude can also be maximum 350 MPa. So, means the residual stress magnitude can be maximum equal to that of the yield strength of the material, and because higher level of the stresses will be leading to the deformation and the yielding of the material, and the residual stress will be eased out, and that is why the maximum magnitude of the residual stress which can be retained in the weld joint will be equal to the yield strength of the metal. So, higher the strength or the yield strength of the metal, greater will be the residual stress. And another aspect is that the hardness of the material, because the chemical composition will be affecting the microstructure, and that in turn will be leading to the change in mechanical properties, and the mechanical properties will have the effect on the performance of the joints. Like if the ductility is very less, if the material hardness is very high, under the tensile residual stress conditions, the weld joints will be showing the embrittlement as well as the cracking tendency. So, increased cracking tendency will be leading to the reduction in the weldability of the material. So, like I have explained, like the greater chemical heterogeneity if is existing, then it will be leading to the liquefaction cracking and the solidification cracking tendency. And similarly, in case of the steels, the carbon content and the alloying elements directly affect the carbon equivalent, which in turn affects the hardenability of the steel, and increased hardenability of steel will be affecting the embrittlement or the low ductility, low toughness tendency of the weld joint. The chemical affinity is the another important aspect that I will explain little bit. Like if there is a metal system which is subjected to the external heat for the fusion. So, at a high temperature there will be environmental gases like oxygen, nitrogen and hydrogen. So, the way by which metal has the affinity to these gases which are present all around during the welding, it can lead to the formation of the oxides of the metal or the nitrides of that given metal, and these oxides and nitrides may be refractory in nature. These may be hard and brittle, these may interfere with the fusion of the metal. So, these will make the welding difficult. At the same time, these oxides of the metal oxides and nitrides will be of the in general they are hard and brittle. So, these act as a inclusions if these are left in the weld joint, and these inclusions promote the nucleation of the cracks in the weld metal under the external tensile loading, and thereby these reduce the performance of the weld joint. So, if the metal is having the greater affinity, chemical affinity to the oxygen and nitrogen, then we need much better production, more effective process which can protect the weld metal from these gases, so that the sound weld joint, and for that we need to put in extra efforts and that in turn will be reducing the weldability of the metal. So, metals having the greater affinity to the environmental gases, that will be leading to the reduction in the weldability. Now, I will summarize here this presentation. In this presentation, basically I have talked about the ways by which the metallurgical properties and the chemical properties of the weld metal can affect the ease of the welding or the weldability of metals. Thank you for your attention.